I prefer English.
אבל לפחות את ההקדמה נכתוב בעברית, ואתה תבין. אנחנו שמחים מאוד לארח היום את יאיר קרמון מאוניברסיטת סטנפורד. הוא עושה הרבה עבודות במשין לרנינג, והוא יספר לנו על אחת מהן לפחות.
Okay. Thank you very much. I'm very happy to be here. So in this talk, we're going to explore some fundamental limits of machine learning and use the insights that we get from that in order to design new and better algorithms. I'm going to use this term fundamental limits quite a lot. So to motivate what I mean by this, I would like to start with a couple of examples that are outside of machine learning. So the first example is heat engine design. You want to convert heat into energy. And what Carnot discovered is that there is a fundamental limit to the efficiency of heat engines, where the efficiency is the fraction of the heat that you can turn into energy. And this is the fundamental limit in the sense that it's independent of technology. So no matter how sophisticated your heat engine is, even if you make it very, very shiny and use a deep neural network to design it, it will still not run more efficiently than Carnot's limit. Another example is communication over a noisy channel. And what Channel discovered is that given a statistical characterization of the communication channel, there is a fundamental limit called the channel capacity of the rate of reliable communication that's possible with any error-correcting code. And again, this is fundamental in the sense that no matter how good your decoding algorithm is or the code design is, you will just not be able to communicate reliably faster. So even if you use a quantum computer to decode it and there's a blockchain somewhere around it. So why are these fundamental limits important? First of all, they're just beautiful mathematical facts and their proofs are stunning. But more than that, fundamental limits help us advance technology. So first of all, they tell us what not to try to do. So don't try to build a heat engine that's more efficient than Carnot's limit. But they also give us valuable hints to what we should be doing. So for example, something called supercritical steam generators run very close to the Carnot limit. And similarly, information theorem, particularly the channel coding theorem, gives us very important guidance on how to design error-correcting codes that approach the channel limit. But more than that, fundamental limits facilitate paradigm shifts because they basically set a certain set of rules of the game and tell us what happens. And if we don't like the game, we can start to try to change the rules. So for example, with heat engines, you usually have fuel and you burn it and then you turn the heat into energy. But you can also extract energy from fuel directly, chemically, using fuel cells, and then they can be much more efficient than the Carnot limit. And similarly, expressions for channel capacity come from characterizations of certain physical media of communications, and by building new media of communications, we can achieve different relations between the input and the output, which of course have their own channel capacity, but it can be much higher. So inspired by these sort of results, a major goal of my research is to try to understand fundamental limits of machine learning. So in a crude level of abstraction, what is machine learning? It's a methodology that allows us to design new algorithms, and to avoid confusion, I'm going to call these algorithms predictors, using data. So how does it work? First, we define a class of candidate predictors, and we define a function, a loss, that takes in a predictor and the data and tell us how well it performs. And then we search over our class of predictors, and the best predictor that we find according to the loss is the one that we use. And this search over the class of predictors is, of course, a problem in mathematical optimization. And there a very, very important bottleneck is computation. And in some sense, theoretical computer science is all about the study of or search for fundamental limits in computation, where they're sometimes more prosaically known as lower bounds. But still, they are fundamental. And the specific optimization problems that we encounter in modern machine learning are more often the non-convex optimization problems, and our understanding of fundamental limits for non-convex optimization is lacking. So in the first part of this talk, we are going to tackle this by looking at the complexity of finding approximate stationary points, so points that have small slope or small gradients. And when I'm saying complexity for the complexity theorists out there, I mean oracle complexity, which I will define more carefully. But the type of fundamental limit that we're going to prove is that for general algorithms for finding stationary points, there is no beating gradient descent, which is a very basic and important algorithm for non-convex optimization. However, this can be a bit surprising because in convex optimization, there are techniques like Nestrov's momentum which strictly outperform gradient descent. So gradient descent is not an optimal algorithm for convex optimization. And by understanding this fundamental limit, we can identify a basic assumption about the smoothness of the function that isn't directly related to convexity and is much weaker than convexity, under which we can use these momentum techniques and design an algorithm that is much more efficient than gradient descent. So this would be the first part of the talk. In the second part of the talk, we're going to talk about a different aspect of machine learning, where the bottleneck is how much data do I need to see in order for the predictor that I find to actually perform well on things that I haven't seen yet. And in modern machine learning, we often don't want to perform well on average. We also want to perform robustly. And in particular, in the second part of this talk, we're going to talk about a robustness property called adversarial robustness, where we want predictors to be invariant to tiny perturbations of the image that you can't even see. So exactly this situation where first you classify as a cat and then you classify as guacamole is something that we would like to avoid. However, getting this sort of robustness can come at a cost. So we will discuss a very, very simple Gaussian model where just getting standard average accuracy is easy in terms of the number of examples that we need, but getting this robust accuracy can take us arbitrarily more examples. However, by studying this fundamental limit, we see that actually many of those examples can be unlabeled, which is great news because the most expensive part is usually getting the labels. So with unlabeled data, we prove that with only a constant amount of labeled examples, we can still attain this adversarial robustness. And this is, again, in a very, very simplified model. But then we take this model into practice and use the insight that we get from this to design an algorithm that improves the state of the art in kind of the most popular robust image classification benchmark. So this will be the second part of the talk. Okay, diving into the first part of the talk, which will be a little bit longer and more technical, and is joint work with John Ducci, Oliver Hinder, and Aaron Sidford. I would like to motivate you just a little bit more by coming back to this caricature of machine learning and talking about this search problem. So in quote-unquote classical machine learning of maybe the previous couple of decades, most of the focus was on linear classifiers and convex loss functions, which created convex search problems in terms of the predictors. And these problems are very nice because you know you can find the global minimum in polynomial time. And more than that, there is a very strong suite of algorithms for finding these solutions. And moreover, there is a very comprehensive theory of optimality of algorithms that tell us that in some sense we know the right algorithm. So I wouldn't say that convex optimization as a whole is solved, but this particular problem of finding linear predictors for minimizing average risk is in pretty good shape. However, in modern machine learning, the predictors that we use are much, much, much more complicated and non-linear. And composed with the loss functions, we get non-convex optimization problems, and there things are less clear. So we do have some algorithms, and we run them, and we're pretty proud of the results that we're getting, but it's not clear if they are the right algorithms. So there is not a theory that clearly tells us that there is not another non-convex optimization algorithm hiding somewhere that is not much better than the things that we're trying to do. So trying to understand this, trying to understand if we have the right algorithms and what can we improve is the major motivation for the first part of the talk. So to set things up just a little bit more formally, we have a function f from r to the d to r, and the goal is to find an x that minimizes the function x. So in machine learning, this x would be exactly this predictor that we're trying to find. And in engineering more broadly, we can just say, okay, we have a parameter or something that we want to design. We have a measure of how good it is, and we want to find something good. So mathematically, the object that we would ideally like to find is some x such that there is no other z that is better than x by more than epsilon, so an approximate global minimum. Unfortunately, this is computationally intractable. So in terms of the number of interactions with the functions that I will need, this will be exponential in a dimension, so it wouldn't be suitable for the high-dimensional problems we see in machine learning. And even just deciding if a point is a local optimum or a very degenerate saddle point can be, in general, computationally hard. Instead, what we're going to focus are points that are epsilon stationary, such as this point, and also this point. So the norm of the gradient is less than epsilon. And one very important thing about this is that it is computationally tractable, and we will spend a bunch of time trying to understand exactly how tractable it is. But I probably should first say, why are stationary points even interesting? Because I just said that we want to find good points. So the first answer is that if you were already willing to settle for a local minimum, an epsilon stationary point is the next best thing, because it's basically giving you a local certificate that you're not improving the value of the function much around the point that you found. Second of all, if you're not willing to settle for a local minimum at all, there are several classes of problems where finding a stationary points guarantee that you've found the global minimum. So of course this is true for convex optimization, but that's not very surprising. However, other problems that are non-convex, such as matrix completion and phase retrieval and various representations of Markov decision processes, also have these properties, sometimes under statistical assumptions of the data. And of course, for neural networks, the picture is much more complicated. But under certain strong assumptions about the neural networks, we can tell similar stories there as well. And finally, another reason to think about stationary points is a sort of a yardstick to compare different algorithms. So in optimization, for many years, the tradition was that if you had an algorithm and you wanted to prove mathematically that it is a sane algorithm, you prove that it converges to a stationary point. So proving something about the rate at which it converges to a stationary point is kind of something more refined. And as a thought experiment, suppose I have an algorithm and I can prove that it converges to a stationary point in n iterations, and then Tomer comes up with an algorithm that converges in square root n iterations, that things like this can happen sometimes, then Tomer's algorithm sounds very interesting and we would like to try it out. So with that in mind, I would like to introduce one of the main characters in our story, which is gradient descent. It's an extremely simple algorithm. You compute the gradient at the point, you subtract it from your current iteration, and then that's your new iteration. So visually, it looks like going downhill. And gradient descent is an extremely important algorithm, and I would like to argue that the two first-order reasons why it's an important algorithm are these, that it's general and scalable. So general means that whenever we have an objective function and we can compute gradients or even estimate gradients, we can apply gradient descent. So if somebody comes up with a new, very, very crazy neural network tomorrow, we can still use gradient descent on it. And if in a few years from now we're tired of neural networks and we come up with something else, as long as it's differentiable or approximately differentiable, we will be able to use gradient descent. So this is very general, but more than that, it is computationally scalable to high-dimensional problems. So usually, the time to compute the gradient is the problem description size, but if you use stochastic estimation of the gradients, it can even be much smaller than the problem description size. So this is perfect for machine learning, where the scale of the data increases all the time, and we want a relevant algorithm. More than that, gradient descent is capable of finding stationary points. So if you assume an upper bound on the initial suboptimality of the algorithm, so you can't just go downhill forever, and you assume that the gradient is a Lipschitz function, so here it's one Lipschitz, so it's kind of contractive, then it's quite easy to prove that in 1 over epsilon steps of gradient descent, you will arrive at least one point that is epsilon stationary. So this means something about the convergence of gradient descent. And now there is a very natural question: can we beat it at its own game? So under the same set of assumptions, can we find another algorithm that finds an epsilon stationary points in less than 1 over epsilon squared iterations? And there is some reason for careful optimism here, because for convex functions, the answer is yes. OK, so an outline for the rest of the first part of the talk. First of all, in order to say something about all algorithm whatsoever, I need some formal model of what is an algorithm. And I will do this using this notion of an oracle. With this notion in mind, we will be able to state a fundamental limit, which is kind of a negative result, that there is no beating gradient descent in its own game. Any algorithm would have complexity at least 1 over epsilon squared. And we will show a proof sketch of how we prove something like that. And then we will remember what we said about convex optimization again, and the fact that these momentum techniques are really useful. And using a principle that we call convex until proven guilty, we will show how to bypass this limit with a fairly weak assumption on the smoothness of the function. And then we will quickly mention also lower bounds in the stochastic case where the gradient has noise in it. Was there a question somewhere? Sorry. No? OK. So the oracle model. So I'm going to call an algorithm any iterative procedure that asks about a point in RD and gets back from this oracle local information about the point. And since I want to encompass a very large class of possible algorithms, I will say that this information is any local information about the function at the point x. So it could be the value of the function, and the derivative of the function, and the second derivative of the function, the third derivatives, and so on. So this is what the oracle gives me back. And now I have a very natural notion of complexity, because I can just say that the number of queries to the oracle before one of my queries is an epsilon stationary point is the complexity of minimizing a particular function with a particular algorithms. And for a class of functions and a class of algorithms, we're going to play a game where somebody gives an algorithm and then an adversary gets to pick a function from the class of functions and get the worst function for it. So overall, the complexity is the performance of the best algorithm on the worst function. And what are these classes of functions and algorithms? Yes?
אתה יכול לנמק למה אתה בוחר את למה אתה מגביל את עצמך לאורקל כזה? הרי בייחוד אם הסימוכיות לא תהיה מאוד קטנה, אז האלגוריתם כבר ביקר באיזה 20 נקודות לפני זה, למה לא להשתמש בהיסטוריה של האלגוריתם גם?
So it can use all of the history, right? Like it can do any computation of the information it got so far. I haven't constrained the computation at all. It can do absolutely crazy things.
לא רק בהינתן X, אלא בהינתן X בכל מה שהוא רק...
Yes, and more than that, when I'm saying all algorithms, I'm even allowing algorithms that can use randomness in deciding what's the next point to query. I'll also talk about a slightly smaller class of algorithms that are deterministic and first order. So deterministic just means that it's a fixed function, but it can still use the entire history. And first order means that it only uses the value of the function and the gradient of the function, which will just make for algorithms that are much more natural and feasible to actually implement. For classes of functions, of course, the most interesting one is the one that gradient descent does something on. So these are the class of function with bounded initial suboptimality and Lipschitz gradient. But I will also talk about classes of functions where higher order derivatives are Lipschitz, and this will allow us a little bit more flexibility. So this...
לגבי החישוביות של הנגזרות, זה O של 1 ובאיזה דיוק אתה מקבל אותם?
So right now I'm kind of ignoring accuracy issues, so I'm just assuming that we get it accurately. In terms of the computational cost of actually implementing such oracle, of course it will scale with the level of derivatives that I'm using. For lower bounds, it's not very important, because if I prove a lower bound for anything that has all of this information, then I kind of know that I have nothing to do. For upper bounds, we will of course be much more careful, and we won't only give upper bounds on the oracle complexity, we will also give upper bounds on the runtime. And in particular, the runtime of computing a gradient will usually be something proportional to the problem dimension, and we will write down sane algorithms that are kind of numerically stable. In fact, our algorithms won't do essentially anything that accelerated gradient descent doesn't already do.
So when you speak of gradient to the k, you mean that it's one Lipschitz. You think as a function on d to the k dimensional space?
Yeah, I basically mean that if you take the difference in 2 points and look at the appropriate operator norm.
Which is all the k derivatives.
So it's just like a tensor operator norm. Yeah. Okay, and of course the question that we want to answer is how does this complexity depend on epsilon, where epsilon is the accuracy to which you want to solve the problem, or more specifically, how small the gradient should be. Okay, so now with these notions in mind, we can start to build up our results. So when we assume that the gradient is Lipschitz, we know that gradient descent has oracle complexity 1 over epsilon squared, because each iteration of gradient descent is exactly one question to the oracle. So the first place in the literature that I know of this result explicitly is Nestorov lecture notes from 98, even though I'm pretty sure people knew about it before. If anyone knows a reference, I'm very curious. What was not known, if you can get any better oracle complexity under these assumptions, and what we prove is that the answer is no. So for this class of all algorithms, even the one that can have completely exact second-order derivatives and third-order derivatives, and even if they can use randomness, we show a lower bound of 1 over epsilon squared. And we'll, of course, have a lot of more room in the table, so there will be a lot more results coming up. But I would like to talk a little bit about how we prove this. And first, I would like to put it somewhat more in the context of the existing literature. So for convex optimization, there is beautiful literature starting from the 80s about the Oracle complexity of optimization. And there, of course, we usually talk about the complexity of finding an epsilon global solution because it's convex. And as I said, their gradient descent is not the optimal algorithm. And many of the techniques that I'm going to describe are what we do to adapt these ideas for lower bounds for convex optimization into the non-convex world. For non-convex optimization, there is less work. So two relevant lines of work are a paper by Vavasis from '93, where he proves a lower bound for deterministic first-order algorithm, which is 1 over square root epsilon. So, of course, this is not tight, but it is a lower bound. And Curtis, Gould, and Twant have a series of papers where they look at specific algorithms like gradient descent or families of algorithms that look like gradient descent, say with line search and things like this. And they prove that for them, the analysis is tight. So for them, the 1 over epsilon squared is tight. But of course, there are many, many algorithms that don't fall under what they prove. OK, so how do we prove these results? So the key technical difficulties is that algorithms can be crazy, as the picture illustrates. So they can take all the information they have so far, they can encrypt it, and then they can break their own cipher, and then they can play Sudoku on it, and flip some coin and ask the next question. So how do we say anything about what they can and cannot do? So the first step in the proof is imposing temporary structure on the algorithm. So we're going to make an assumption about how the algorithm operates, which is actually a very practical assumption, but it will only be for the sake of our proof. With this assumption in hand, we will design a single bed function from R to the D to R that is going to exploit this structure. So the way it's going to work is that this function has this form of a chain. And nice algorithms, when they operate on the function, they start at the first place on the chain. And there, they can only query points with gradient larger than epsilon. And moreover, the information that they gather from this query will only move them to the next step in the chain, and so on. And only in the iteration d plus 1 will they finally be able to query a point such that the gradient is less than epsilon. So if we're able to build such a function and are able to take the dimension d to be 1 over epsilon squared, then we are able to show that all the nice algorithms cannot take less than 1 over epsilon squared iterations to find a stationary point, even for this one particular bed functions. But now what we actually want to do is talk about all algorithms, and definitely a single function is not going to defeat all algorithms because there's always the algorithm that starts out by querying the global minimum of that function. But what we're going to do is we show that with a simple random transformation of this one bed function, since we built it carefully, we can force every algorithm to essentially behave like a nice algorithm, and this will give us the result that we want. Okay, so this is the sketch of the proof, and now let's talk a little bit more. Oh,
so
yes.
in principle, if the dimension is fixed, then the lower bound is not arbitrarily small.
So that's right. So our constructions in the lower bound require us to have a dimension that is roughly the same as the number of steps that we want. So you should think about it if you're willing to run for a number of steps that is kind of similar to the dimensionality of the problem that you want to solve, which I would argue is the usual case kind of in machine learning, then our lower bounds are valid. And we will show some runtimes in some slide of the talk where if you allow dependence on the dimension, you can actually do a little bit better. So in some sense, it's essential to have these high dimensional lower bounds. Yeah, that's a good catch. So what are these nice algorithms and bed functions? So for the definition of nice algorithms, we're adopting this notion that Nesterov had of saying that an algorithm is nice if every point that it's querying is a linear combination of the gradients that it has seen so far. And a gradient descent, of course, does it because it just adds the gradient at every iteration, and also gradient descent with momentum and LBFGS. They're all nice algorithms. So this is definitely a reasonable assumption, but it's just temporary. So this will make the initial point 0. But again, this is only temporary, and afterwards we will handle everyone. But you can kind of think about, I'll just give you 0 for free, and from there you will do what you want, right? So like, assuming that the initial point is 0 is not a very bad assumption anyway. To define a bed functions, we actually wanted to satisfy two properties that generalize the properties that Nesterov had in a particular construction. So the first one says that if you have a sequence of 0 coordinates going from I to the D, so all the way to the end in the query, then the gradient you get back for this query, the coordinate I plus 1, is also going to be 0. And of course, if you just apply the same reasoning, it means that also coordinate I plus 2 of the gradient is going to be 0, and I plus 3, and so on until D. So this is the first property. And the second property is simpler, that if the last coordinate of the query is 0, then the gradient is larger than epsilon. So let's see what's the interaction of this first property and the span assumption. So we're going to do a little illustration where the first row is the querying that we make, and the bottom row is the gradient that we get back. So the first iteration, of course, we have to query 0, because 0 is the only point in the span of nothing. And then by the first property, it means that the only coordinate of the gradient we get back that is not 0 is the first coordinate. So now what do? We have to query something in the span of the first standard basis vector. So only the first 2 coordinates of the gradient we get back are not 0. And you can kind of see how it goes from there. Every iteration that we get, we uncover one more coordinate of the gradient. So this is kind of the chain mechanism that I said. And all the way through the end, the last coordinate was always 0. And now we can use the second properties and say that throughout the runtime of this algorithm, all the query that it made got back points that had gradient larger than epsilon, which is kind of exactly what we wanted in order to make the algorithm fail, right? So we can say that the complexity of the entire class of nice algorithms, as we've defined them, and this single bad function is larger than the dimension D. Well, I saw a question there, or? OK. So this is very close to what we wanted, but it's not exactly what we wanted, right? Because we wanted a class of functions here. So to turn it into the complexity of a class of functions, we just need to find such a bad f that is a member of the class of functions. So bounded initial suboptimality and Lipschitz gradient. So as a first attempt, we can look at that particular construction that Nestor had. And by making a small tweak to that particular construction, we are able to take the dimension D to be roughly 1 over epsilon. And that means that the complexity of all the functions in the nice algorithm is larger than 1 over epsilon, but this is not what we wanted, because we wanted 1 over epsilon squared. And that shouldn't be very surprising, because this is a convex function, and we already said that convex functions aren't going to cut it. So instead, this is the part that required a little bit of inspiration, and we came up with this function. So you see that we still have this form of a chain where we couple together only consecutive coordinates. And this is really helping us improving all of those properties and controlling the Lipschitz constant. But we're also using these element-wise nonlinearities, psi and phi, or psi-phi for short, that are basically the functions that you see here. So of course, we have equations for them, but they don't really matter, because anything that would look like this is going to work. And what we're able to do is to show that using this function, we can scale the dimension up to be up to a constant, of course, 1 over epsilon squared. And this gives us the lower bound that we want. So now we know that any nice algorithm whatsoever will require at least 1 over epsilon squared iterations. OK, but the last step is to go from the nice algorithms to all the algorithms. So there, the mathematical details get a little bit subtle, and we build on a technique by Woodworth and Srebro, and which we slightly revise and improve. And the basic idea here is to use a random coordinate system. So more formally, instead of using f of x, we use f of pi of x, where pi is a random orthogonal projection from a higher dimensional space to R to the D. And by using this random coordinate system, we're basically kind of giving the algorithm 2 choices. You can do stuff in the span of the gradients, which you've already seen, and then you'll be a nice algorithm. Or you can pick your own direction that doesn't have anything to do with what you have seen so far. But then, kind of by a careful probabilistic argument, we can show that these new directions are essentially spherically uniform vectors in the original coordinate system, and therefore they have very small components, and we build our construction robust to queries that are almost 0 outside the spans. And using this, we get what we wanted, that the complexity of all the algorithms whatsoever is lower bounded by the complexity of nice algorithms up to a constant. So this was the sketch of the proof, and now we go back to the table of complexity, and we know that the kind of optimal complexity for finding stationary points for this class of functions is 1 over epsilon squared. But of course, we don't want to stop there. We want to think about how to bypass this. So one thing you could do is look at functions where the Hessian is continuous and not just the gradient. And what Nesterov and Polyak discovered is that there you can find the stationary point faster than gradient descent. So you can do it with epsilon to the minus 3 over 2. And this is with a version of Newton's method. And with just rescaling of the same lower bound that I described, we can actually prove that this is also optimal. So there is no beating Newton's method at its own game. But there is still something missing here, because gradient descent is a first-order algorithm, and we spent some time explaining how scalable they are. But Newton's method is a second-order algorithm, and it doesn't have these scalability properties because you need to evaluate the Hessian and do linear algebra on it in every iteration. So one question that remains open from this is, can we take these smoothness assumptions, which are kind of like weak, and build a first-order algorithm that only uses the gradients, that does something better than gradient descent? So for example, can you assume that the gradient and the Hessian are continuous and do something better? And the answer is yes. So in a paper by our group, which came out essentially at the same time as a paper from another group, Agarwal, Bulins, Ellen Ju, Ma, and Elad Chazal from Princeton, we developed a first-order algorithm that is also completely computationally implementable, and kind of at every iteration, the main complexity is just computing the gradients that finds us epsilon stationary points in less iterations than gradient descent. And in this talk, I want to talk about a slightly later work that uses a technique called convex until proven guilty, which has a number of advantages, and one of them is that if you have even additional smoothness, so the third-order derivatives are continuous, then you're able to find a stationary point even faster.
Can you remind us why the 1 over epsilon square lower bound does not apply to these algorithms?
Yes, because we are making stronger assumptions on the input. So we are assuming that the class of functions we're working on now is smaller. So these are functions that not only the gradient is continuous, but the second derivatives are continuous. So what is this convex until proven guilty idea?
First order, you mean that the algorithm is only using the gradient, even though you assume the properties of the higher gradient?
Exactly. So what is this principle? So it's not even a meta-algorithm, it's more like a meta-proof. So imagine you have some method M that is provably more efficient than gradient descent on convex functions. So here is the radical suggestion. Take this method M, apply it on the function f, and don't worry so much if the function f is convex or not. What can happen? Either it just works as intended for convex functions, and then you're happy because it converged fast, or it fails to converge fast, right? Because the function wasn't convex, so the algorithm stalls. But the key observation is that algorithms that are provably good for convex functions don't really require the function to be convex everywhere. They require the function to be convex along the iterations of the algorithms. So by failing, the algorithm gives you a proof of non-convexity, which is something that we can exploit. So let's see how we can exploit it. We start at a point, and we're going to run our method, but we're going to see if our method converges as it should. And then everything looks good in the beginning. The function looks convex, the gradients are getting smaller, but then all of a sudden, the function doesn't look convex anymore, and the gradients got bigger. And then the key observation is that we can go back to our iterant and find a pair of points that are witnesses to the non-convexity of the function, which means that when you connect them by a line, the function is above them. And then with some analysis, we prove that necessarily there exists a point there that has negative curvature, right, along the direction of these points, which means it's sloping downward. And then we can bring into action this assumption about the continuity of the Hessian. Because if the Hessian is continuous, and you have a single point where the second order expansion is sloping downwards, you will necessarily, by continuity, be able to find another point where the value of the function decreases substantially. And this is kind of the silver lining of proving that the function was not convex. And this allows us to basically start again at the new point. So by using this idea and Nesterov's accelerated gradient descent and a gadget called the proximal term, we are able to get these algorithms that run in time epsilon to the minus over 7 or epsilon to the minus 5 over 3. Or now when I'm saying time, I mean this times the time to compute a gradient. And one very important thing to point out here is that at no point am I computing the second derivatives. So I'm just using basically Nestov's accelerated gradient descent, where I'm monitoring the progress, and when the progress is too slow, I am kind of looking at the iterates I already got and extrapolating one more point from them. So I'm not doing anything very crazy with the iterations of the algorithm. Okay, so after we came up with this principle, a number of other works also used it to design new algorithms. So Jean and Trepali and Jordan also used accelerated gradient descent, but when it stalled, instead of using this proximal term gadget, they just gave it a little kick, and it also worked, so with random perturbations. Oliver Hinder combined it with the cutting plane method, which is another very important method in convex optimization, and this allowed him to get a running time that does depend on the dimension, but the epsilon dependence is a little bit better. So for sufficiently low dimensional problems, this would run faster. For high dimensional problems, it would be slower. And finally, Royer and Wright used a very, very classical algorithm, which is Newton's method, where every Newton step is computed with conjugate gradient. And conjugate gradient works great when the Hessian is positive semi-definite, but doesn't work when the Hessian is not, so it doesn't work when the function is not convex. But they have shown that when conjugate gradient stalls, they get this certificate of non-convexity that allows them to make the extra progress. Okay, so of course, maybe a pretty natural question at this point is, were you actually smart enough with these algorithms? Maybe we can push it even further down. So one thing that's not hard to imagine is that you cannot beat epsilon to the minus 3/2, because if you throw in this assumption, it really doesn't help, and the lower bound still holds. But we can say more than that, because if we restrict the class of oracles to the first order oracles, we can prove stronger lower bounds that nearly match the upper bounds that we have. So they don't match exactly. There is some gap, and I wrote it here in decimal, so you can evaluate the gap for yourself. So we know that the optimal rate is somewhere in this range, and this is a fairly small range.
Again, what is the additional assumption?
So now I'm assuming two things that I haven't assumed before. So the first thing that I'm assuming is that the information that you get back at every query is just the value of the function and the gradient, not everything else. The second thing is that for technical reason, we also need to assume that the next query is a deterministic function rather than a randomized function. But this is kind of like a technical gap right now. But of course, the other assumptions are crucial, because without them, we could do better. Okay, so I mentioned we also have lower bounds for the stochastic setting. So this is joint work with slightly different authors, Yossi Orgevani, John Ducci, Dylan Foster, Nati Srebro, and Blake Woodworth. And here we slightly change the definition of the oracle to give you back basically a noisy quantity that on expectation is the gradient, but has bounded variance. And what we know about stochastic gradient descent in this setting is that it finds an epsilon stationary point in 1 to the epsilon the power of 4 iterations. And what we prove is a matching lower bound. So again, there is not beating stochastic gradient descent at its own game. And the way we do it is that we decompose this quantity into the product of the deterministic rate that we just talked about, and a noise to signal ratio, sigma squared over epsilon squared. And what we do is we take this chain construction that we had, and we build a stochastic gradient estimator for this chain construction, that what it does is with probability epsilon squared over sigma squared, it cuts the link in the chain. So to move every step in the chain, you need roughly sigma squared over epsilon squared queries, which exactly multiplies your complexity by that factor.
What does it mean to cut the...
Okay, so there I would have to go into more mathematical details, but roughly it means that that coordinate of the gradient, which was supposed to still be non-zero, now becomes 0, because essentially we multiply it by 0, and then in the rare event that we don't multiply it by 0, we amplify it just to make things unbiased, and then we're being very careful about the variance. Okay, so
how maybe you can answer it at the end if you want, but how does it work with the fact that the stochastic gradient descent is better in practice than gradient descent, as much as I understand?
So you might be referring to this issue that when people just kind of naively evaluate exact gradient descent, they arrive at solutions that generalize somewhat worse than solutions that use kind of noise during the training. Mm-hmm. So, I mean, these are tricky aspects of non-convex optimization, which this theory kind of doesn't see because it's kind of too broad grained, but you can think about you have different minimum points or stationary points that you can converge to, and they're not necessarily all created equal. So to summarize this part of the talk and to put it kind of a little bit into context, now we come back to this table and we add stochastic gradient descent with the epsilon to the minus 4 here, and this was kind of the picture before our work, and we added several things to these pictures, and there are a number of conclusions we can make. So the first one is there is this separation between what you can and can't do without the noise. And the second one is the separation about the smoothness assumption. And I think kind of a very important implication of this work is for people that are trying to design these new general algorithms and want to prove something about their algorithms. And we're basically telling them what kind of assumptions that you can try to use and what kind of assumptions you shouldn't try to be using. So if you want to do something that does better than gradient descent, you better assume something about the smoothness other than this continuity of the gradient. And similarly, we're saying what you can and cannot do with only first-order methods, because we also have this separation between epsilon to the minus 3 over 2 and epsilon to the minus 8 over 5, which, by the way, holds even if the order of continuity here is anything. So fourth order, fifth order, this lower bound still holds. There are a few open questions. So exactly characterizing this rate is still open, even though the gap is fairly small. And another question is this issue, do we really need to say it only for deterministic algorithms? So I believe it should be true for randomized algorithms, but there are some interesting technical difficulties in order to actually get it to work. And so we finished with the first part of the talk, which talked about the kind of computational bottlenecking optimization. The second part of the talk is more about statistical bottlenecks. And the connecting theme is, again, that we have these fundamental limits, and we bypass them to get better algorithms. Any question before I?
Is there any results about adding further assumptions to the
Stochastic case?
Yes.
Yes. I don't have time for them. But you can do interesting things with variance reductions, in the stochastic non-convex case, which are kind of qualitatively maybe even more dramatic than what you can do in the convex case. And we have lower bounds for that too. You're welcome to our paper or talk to us later. So the second part will be less technical and shorter. It's joint work with Aditi Raghunathan, Ludwig Schmidt, John Ducci, and Percy Liang. And to motivate it, I would like to talk about this issue of robustness in machine learning more broadly. And I think much of it starts with the fact that usually we don't just minimize an abstract loss, but we minimize an average error of fitting the input X to the target Y. And we want to do a lot of things with this paradigm. So we want to do digital content recommendation to sell ads, for example. We want it to do autonomous driving. We want it to do important societal decisions like who gets a loan. And of course, we want better healthcare. But now there is the question, is doing well on average enough to actually get these things to be as performant and as reliable as we need them? So for digital content recommendation, maybe the answer is yes, because your accuracy or your click-through rate are essentially proportional to the amount of money you make, and if the distribution changes, you can retrain your model. So maybe it's okay, maybe there are some other considerations there as well. I would argue that, for example, for autonomous driving, it's not enough, because if your car does well on average in Arizona, that's not going to convince me to drive it in Israel. I would want it to do well under a variety of weather conditions and geographies and other drivers on the road and times of the year and different years. So all of these things, we should take them into account. And similarly, of course, for these other types of problems. And kind of the high-level issue is that we need to perform well across many environments and not just on average across any particular environment. So there's not a single thing you could average and give me a number which I will be happy with. So one way to encode this mathematically is introduce a maximization into this minimization problem that we have and say that for the worst-case environment, we want to perform well. And how to do this properly and how to get the robustness that we want is a very interesting question, and I would like to spend a few years thinking about it. But as kind of an initial step and a toy box for these ideas, I want to talk about adversarial robustness, where this is kind of a very, very minimal version of robustness, where we just want to say, look, humans don't care if you move the input just a tiny bit in some normal around the input. So I want to find models that don't care about this either. So here the environments are just these tiny perturbations of the input. But this is actually surprisingly notoriously difficult to guarantee. So as the picture that I've shown before shows, you take this cat, you just change every pixel by roughly the value of the least 3 significant bits, not exactly, but roughly, and all of a sudden the prediction changes completely. This picture is, by the way, from Nicolas Carlini. Yes?
This specifically is like you have, you take the gradient to maximize the loss.
Mm-hmm.
Specifically, so in a
Right, this is what it means to write a max here.
yeah, I know, but it runs and gradient descent to find that point is not anything,
Okay,
right?
okay, so?
It's kind of different.
No, this is what it means to have a max here. I would argue it's not different. So this, of course, raises some security concerns, right? Because what if this was a facial recognition engine? You wouldn't want to let the guacamole in. But you can say, okay, maybe this itself is not robust, because if I... we targeted it. We, as the comment said, we carefully chose the perturbation in the max here to make it mistake for the guacamole. We optimized it. Hmm?
You aim for
I aim for guacamole. That's generally, after living in California, that's what I do. But this is not just like one static image thing. People have been able to create these three-dimensional objects where every angle you look at them, it makes the classifier go wrong. So maybe there is something of a security concern here beyond just this thing. But so this is another picture of the turtle. But anyway, this highlights a deep shortcoming of machine learning models, because definitely humans aren't susceptible to these perturbations. And ideally, we would like our models not to be susceptible to them either. And that raises a very interesting puzzle of how we find models that aren't susceptible to adversarial perturbations. So a popular benchmark for trying to develop these models is a data set called CIFAR10 that has 50,000 training examples from 10 different classes. And we are studying this L infinity norm perturbation with this radius 8/255. And for this benchmark, it's surprisingly difficult to achieve robustness. So if you take a standard state-of-the-art model, it achieves pretty incredible standard accuracy, over 98%. But it will get it wrong each and every time under this robust perturbation model. So worse than random guessing. An important paper by Madri et al. Managed to get robust accuracy that is far from random guessing, but it is still not very good, using a technique called adversarial training, where you target this type of objective directly. So you try to compute the max every time and then take the gradient. And then there was sort of an explosion in literature on this topic, where many, many papers considered adversarial robustness in this particular benchmark. And even though these papers did interesting things like try to train robust models more efficiently, or try to prove that other models that claim to be robust weren't robust, they didn't really improve on that benchmark. One important improvement came this year by a paper by Zhang et al., where they proposed an algorithm or objective for training called trades, which is not this objective directly, but sort of a surrogate, and managed to get better robust accuracy. I should mention, though, that these are upper bounds on the robust accuracy, because this maximization of the error problem is in itself a non-convex maximization problem. And these algorithms don't come with formal guarantees that no one else can do worse. They only come with kind of the guarantees that many, many people tried. So it seems that there is something to it. But these numbers might be somewhat lower in reality than the numbers that we have here. And of course, these challenges motivated a very nice list of theoretical works trying to explain why is finding these adversarial robustness models so hard. And one explanation that I really like is that maybe there is the robust model out there, or I know there is, maybe there is even a robust neural network out there, but maybe we just don't have enough data to find it. So maybe the bottleneck is kind of the information that we have. And what we show is, so they show it in a very simple Gaussian model, which I'll describe in a second. And what we show is that in the same model, we can bypass this fundamental limit using unlabeled data. So what is this model? So the dimension of the input is going to be D, is going to be an important parameter, and we're going to have n examples, but there won't be cats and guacamole. Instead, there will be y uniform or -1 and 1, and x conditional on y will just be Gaussian with mean mu times y and a certain variance, where mu is this certain d-dimensional vector. So it's important that the dimension will be high, but when I pick the parameters in the right way, what's going to happen is that it will be possible using a small amount of examples to find one direction, like this direction, which separates the data. So this is a two-dimensional projection. The y direction will be random just for illustration. And you can see that we get this good separation here, so we get good standard accuracy. But now if we project down the L infinity ball, we see we actually have no robustness, because around each point I'll be able to cross the decision boundary. So it's not robust at all. In contrast, if I had many, many examples in this model, I would be able to get a good separation. I would essentially be able to identify this parameter mu and get a separation that is large enough such that the L infinity ball never moves me across the decision boundary. So with a number of examples, there is a robust classifier here. And what Schmidt et al. Show is if you also pick mu to be a Gaussian random vector, then any algorithm that uses only roughly square root D examples won't be able to find a robust classifier, even if it's a very, very fancy algorithm with a nonlinear learning rule and maybe a nonlinear classifier. It's not going to help. So this is a gap in the sample complexity. But what we show is that you can bypass this gap or fundamental limit by changing the game and allowing yourself to have unlabeled data. And again, this is kind of a fair assumption because unlabeled data are much cheaper to procure. So what can we do with this unlabeled data? So one intuition is that we can already learn a classifier that has this good separation. So we can use it to predict the labels and get pseudo labels. And then we can take the learning rule and apply it all over again using the pseudo labels as well and get something that looks like this. So this is the direction that we got using the pseudo labels. And this is a very well-known procedure in semi-supervised learning that's called self-training. And what we prove is that here self-training with enough unlabeled data and the same constant amount of labeled data, in fact, gives you enough separation in order to be robust. So it indeed kind of bypasses this barrier. Of course, this is a very, very simple theoretical model. And if it's any good, it should give us a prediction for what to do in reality. And here the prediction is do this self-training thing. However, just doing self-training is a little bit too naive. So we start with the first two steps of self-training, where we train a standard model only on the label data, and we extract the pseudo labels. But then we apply in the final stage any of the robust training algorithms that I just mentioned before. In particular, we use the traits algorithm. So we had to come up with a name for this, so we call it robust self-training. And this turns out to work quite well. So if we go back to this CIFAR-10 benchmark, and we add to the 50,000 training examples 500,000 unlabeled data, and we can get 500,000 unlabeled data with 2 graduate students. We did the calculation of how long it would take to label them with labelers. That was quite expensive. And we use kind of the standard methodology for training these robust models with a wide ResNet. What we're able to show is that we improve the robust accuracy by 7%, and we also improve the standard accuracy. So it's not just that we find a different trade-off. And again, we can fairly confidently attribute this to the unlabeled data because we use the same final training algorithm as Zhang et al. With kind of similar parameters. So it's not that we just tuned it differently. In concurrent work, people with DeepMind reach similar conclusions, so it's kind of an independent validation. And we also do experiments on another data set, and maybe more importantly, we do experiments on algorithms that do give you this promise of a lower bound on the adversarial robustness. So they do formally guarantee that nobody will find an adversarial examples. And because robust self-training is this black box procedure, we can basically apply it on these methodologies as well and get a similar performance boost to this 7% that I'm showing here. So to summarize, we looked at fundamental limits for machine learning. We looked at it from the optimization aspect, and we proved you can't beat gradient descent at its own game. But by using another weak smoothness assumption and this convex until proven guilty principle, we designed a new algorithm. And overall, we have now a more complete picture of the complexity of finding stationary points. We looked at it from the statistical perspective and discussed adversarial examples. And there we discussed a very simple theoretical limit that shows that adversarial examples can be very hard, adversarial robustness can be very hard to come by, but using unlabeled data can really help. And we translated it into a practical scenario and managed to promote the state of the art in this particular benchmark. I think there are many other areas where fundamental limits are relevant to machine learning. One thing that I'm very interested in is this notion of robustness, and particularly this approach of solving mini-max problems, which also shows up in machine learning in domain adaptations and in adversarial generative networks and several other things. And there are very interesting questions about fundamental limits here. So from the perspective of optimization, there are questions about what is the cost of introducing this max. And even in the convex concave case, it's not completely clear if you can scale up algorithms kind of sublinearly as you do with SGD once you start putting these maxes in. And of course, in the non-convex concave world, it's not even clear if you can even convert to something like a stationary points. So there are many basic open questions here. And again, for robustness more in general, to me at least it's pretty clear that data is going to play kind of a new and different roles, and understanding what amounts of data and what kinds of data we need in order to find models that satisfy our robustness needs, I think is a very interesting question. So with this, I would like to thank you and take any more questions.
Returning to your example with the guacamole.
Mm-hmm.
If you now use guacamole as an input to the network that you described, will you give guacamole or will you give a cat? Or what effect does this new redefinition of the network bring?
So you're saying that the network is going to get both the picture of the cat and the class guacamole?
In the original training procedure.
But what is the extra information that it gets? So right now in the training procedure, I'm saying, look, this is the picture, the right label is cat. So this is what I know. And then what is like the other information?
So in that case, with a newly developed network, give it an input of guacamole and we identify the cat, right?
We adversarially change the input. We add a tiny perturbation that you can't even see here, but it's there. And that changes the output to big guacamole. And now you want to take that picture and tell it, oh, no, it was wrong. This is actually a cat and not guacamole. Is this the point?
I thought that in your new system, you can increase the volume in the space that you define, okay, in such a way that if you give it something which is slightly distorted, it will really return to the original picture. So it will know, okay, whatever.
This is what I'm trying to, yeah, okay, sorry.
I have a question about the first part. So, I mean, you prove lower bound for a black box model, so basically you construct some distribution to make it out to distinguish between it and some other distribution. And if you perturb the functions, the hard functions you created by some like small Gaussian-like function, small norm, etc., would, like in some sense, smooth it more. Would the same lower bound still hold?
Okay, so we will need to be careful about what is exactly this class of perturbations. I think if the perturbation is by just kicking it with a small linear function, it might still hold, I'm not sure. Definitely if it's kind of jittering, you know, these sine and phi functions, I can think of many perturbations where the lower bound would still hold. So I wouldn't call it like a very, very clear measure zero kind of thing. And you did say something very right there, that it is, we actually prove a distributional robustness lower bound. So sorry, distributional complexity lower bound, where I give you, it's not even a game. Like I choose a function at random, you choose an algorithm, and then there is this lower bound. So yeah.
No, that's the only way to prove such lower bounds, but in some sense. So it is smooth and it does not give an explanation why some other methods can run better than the...
Yeah, I mean, but these are very, very large classes of functions. So you can imagine that the instances you care about are far from the bad instances that I'm constructing. That's so like doing more fine-grained things and more instance-dependent things is definitely an area of research that we're thinking about.